Hello, my name is Dylan, and today I'm going to be talking about the quantum dot laser. So in terms of outline, I'm going to be talking about the history and applications of it, and then I'm going to be talking about the quantum dot laser I designed. So first of all, let's talk about history. So the quantum dot itself was discovered by Alexei Ekimov in 1981 in USSR, and originally it was a cadmium sulfide quantum dot array that he used. So after that, it's been used in multiple applications such as biological analysis displays, photovoltaics, and more. But the quantum dot laser itself is novel. In 1982, quantum dot lasers were first proposed, and in 1994, the first quantum dot laser was made in a collaboration between University of Tokyo and Fujitsu. So the applications for the quantum dot laser are not fully developed because it's so new. So first of all, I'm going to have to talk about them in future terms. So for medicine, for example, laser surgeries often rely on multiple wavelengths sometimes. So having a multi-wavelength laser using the properties of quantum dots can actually save space, time, and cost. For displays, laser projectors are actually becoming more common out there. So having a laser projector that can actually get a specific wavelength using quantum dots can actually create more color accurate pictures. And then for spectroscopy, the narrow line widths can actually lead to less filtering needed for measurements, therefore making these devices less costly and more portable. But the most developed application for quantum dots is telecommunications, which, for example, Renovis, an Ottawa telecom company, has a multi-wavelength laser, and it's useful for low temperature fluctuation reduction as well as narrow line widths because of the quantum dots. So let's talk about the design now, which I went for the 1.3 micron regime, and I'll be talking about a lot of different things along the way. So first of all, operating principle. So how do quantum dots function? So quantum dots confine carriers in 3 dimensions, and therefore they're considered to be zero-dimensional structures. They're usually treated as ideal atoms because of their discrete electron states, shown in the picture on the top right. And the radiative recombination actually happens in this very narrow quantum well because, again, of it can be seen on the right because the quantum dots are so small. In terms of how they actually function mathematically, on the right you can see this equation that has the band gap of the dot itself is equal to the material band gap it's made out of plus this extra energy for the first level of the electron level. And further down we can actually see that this energy is dependent on the dimensions of the quantum dot. So we can keep going and actually see that I actually got heavily inspired by the 1.3 micron InGaAs quantum dot laser that was described as being the first one. It had 20 nanometers in diameter and 10 nanometers in height for its quantum dots. So InGaAs is the band gap in the material I used, and its band gap is as shown. But if we want to reach the 1.3 micron light energy, we need to add 166 millielectron volts. So let's get ready for some math so we can actually start calculating what we need to achieve this energy. So indium gallium arsenide quantum dots actually grow in a pyramidal shape as shown on the right side. These usually grow half of the height compared to their diameter, and their dimensions are usually smaller than they may seem, as I'll touch on in a sec. So the dimensions I calculated are 4 nanometers in height and 8 nanometers in diameter. This calculation is not the same as what I got, what we saw in the laser previously, and that is because these quantum dots, first of all, they're pyramidal instead of cubic in shape or spherical, and also these are the electronics dimensions rather than the physical dimensions. So I'll be sticking to 10 and 20 respectively for height and diameter from now on. So the gain can actually be calculated, shown in this equation at the top, and I assume that the quantum dot dimensions can actually be made with a tolerance of 5% maximum to have the inhomogeneous line broadening. So the difference between the size of the dots releasing having different band gaps is minimized. So I looked at the calculation, and I got a gain of 384 inverse meters and a loss of less than that, so we're going to have net gain. The quantum dots are 20 nanometers in diameter and 10 nanometers in height, but they are 50 nanometers apart. And in terms of the active medium itself, it's 15 microns wide, so we can actually get the gain that we want. 10 nanometers thick, because that's the thickness of the quantum dots, and 10 millimeters long, so we can actually get the power that we want, which I'll touch on later. So for laser diodes, we actually need optical and electrical confinement to get the most efficient laser possible. So I looked at optical confinement first, and well, the active medium is basically a waveguide if you think about it. The gallium arsenide has a refractive index of 3.4, and that acts as a guide. And the aluminum gallium arsenide is basically the cladding at a refractive index of 3.2. So in order to only support the TM00 mode, or the 0th mode, we can use this equation shown, and we find that the thickness of gallium arsenide is needed to be 510 nanometers. Now we can actually look at the electrical confinement, and this is where electrons and holes should only meet at the quantum dots. And the actual device, or the layers, actually lead to this because the aluminum gallium arsenide and gallium arsenide have a larger band gap than the quantum dots made out of indium gallium arsenide. And you can see in the energy diagram on the right the discrete energy states, and the lowest energy state being at 0.95 eV. So this on the left is the zoomed out version of our device, and on the right is the zoomed in version. And I'll just explain a little bit of the reasoning behind the thicknesses I chose. So first of all, gallium arsenide and indium gallium arsenide and the quantum dots being 10 nanometers thickness, I talked about that. We want the 0.95 EV band gap. The P and N region gallium arsenide layers are 250 nanometers each, and that is because we want the waveguide to be 510 nanometers in thickness or in height. Therefore 250 plus 250 plus the 10 nanometers in the center being gallium arsenide as well will lead to that thickness, so we can have only one mode of light. P and N aluminum gallium arsenide also has 500 nanometers each, and that is because we are trying to prevent the evanescent waves reaching the aluminum at the top, because it would start absorbing it, and the substrate at the bottom, because it would draw some of the light from the waveguide. So we want to have 500 nanometers in between as cladding. The gallium arsenide substrate is 625 micrometers, and this is because 4-inch wafers are typically, for gallium arsenide, are typically this thickness, and silicon dioxide and aluminum will have 50 nanometers each for electrical reasons. So in terms of fabrication, I'm not going to go into the doping concentrations, but I will talk about the methods used for fabrication, so MOCVD, MBE, RIE, PECVD, and PVD. We have the elements at the bottom being fed with precursors for MOCVD and MBE. And I'll start talking about fabrication now. So we start off with an N-type gallium arsenide wafer. This gallium arsenide wafer is then deposited with 500 nanometers of aluminum gallium arsenide, 0.4 and 0.6 ratio for aluminum and gallium. And we used MOCVD to deposit this, and we used the dopants shown for N doping. Then we have 250 nanometers for gallium arsenide deposited also using MOCVD, and we use the same dopants. And it's interesting to note that we actually have the aluminum arsenide and gallium arsenide lattice matched. On the graph on the right, we can actually see that lattice matched in order to not have a weird transition between the two materials electronically, which is good. We won't have any strain. And then 10 nanometer tall and then 20 nanometer diameter indium gallium arsenide with the ratio shown islands are made using MBE, using the Stransky-Krastanov method. This actually uses the lattice mismatch, again shown of indium arsenide and gallium arsenide, which is actually beneficial because we have the island formation that we do. Then we have 10 nanometers of gallium arsenide. It's deposited using MOCVD to surround the quantum dots, as shown on the bottom right. And then we have the 250 nanometer gallium arsenide, again, layer deposited using MOCVD, but this time p-doped using the dopants shown, and then 500 nanometers of aluminum gallium arsenide using the p-dopants as well. Then we can actually use photolithography, and we make a mask area on top of the basically active medium that we wish to make, 15 microns by 10 millimeters in area. And we develop everything else, and we got to make sure that the short side, so the 15 micron side, is parallel to the crystal axis, and I'll explain that in a little bit. We basically want to cleave later on. And then we dry etch down to the gallium arsenide substrate using RIE, and we make this mesa structure. Then we use MOCVD to deposit aluminum gallium arsenide, first p-dope and then n-dope for this electrical confinement. And we deposit 50 nanometers of silicon dioxide using PECVD. Again, we use photolithography, but this time we use the negative resist using the same mask to develop only the active medium area. Then we wet etch with hydrofluoric acid to remove the central silicon dioxide, and then we sputter on 50 nanometers of aluminum at the front and the back to make the contacts using PVD. Finally, we actually dice or cleave the wafer in parallel lines, basically parallel to the active region, every 5 millimeters, sorry. And then we cleave, not dice, because we want high quality facets. These will be separated by 10 millimeters. We then, once we have the chips, we coat one side with aluminum for 100% reflection, and the other side with 40% reflection dichroic thin film materials. So the performance is going to be touched on in a second, but these are basically the bigger equations that I use to actually calculate some of these values. And these are the parameters. So first of all, the threshold current comes to 19 milliamps. The spontaneous and stimulated emission lifetimes are shown. We can see the stimulated emission lifetime is much shorter, which is great because that means that the gain will be coherent. So it's a laser. The optimal transmission is 0.6, so that's why we wanted 40% reflection coating for the dichroic side. And then we have a power output of 31.7 microwatts, which seems odd, but I'm going to touch on that in the discussion later. longitudinal mode spacing comes to 4.4 gigahertz, and the transverse modes end up just being the 0th mode. So in terms of laser performance and specifications, we have to deal with the divergence as well of the laser. And well, I use full angles for this. The planar mirror cavity didn't let me use the confocal equations that I would like to use. So I thought, okay, this is a waveguide, so maybe the fiber acceptance angle formula could be used, which is shown below. And well, it gave me 180 degrees plus of divergence, so that didn't work. Okay, so the waveguide, it's just much narrower than the wavelength itself, so maybe it's just a slit issue divergence. So let's use that equation. But that gave me more than 180 degrees as well. So I settled on the full width half maximum being at 109 degrees. So I simulated this device using Zemax, and all the dimensions were accurate, all the refractive indices were accurate, and the mirrors were accurate. And I used the non-sequential ray tracing algorithm in Zemax, and you can see all the objects I had. I used 300 Gaussian sources, placed basically one per quantum dot column. So looking at it from the front, this is what it would look like in the image. Each Gaussian was 5 nanometers in beam radius, basically because the quantum dots are about that size. And I expected the light waves to mix. Now the 3 detectors that I used were placed at 0 centimeters, so the output at 1 centimeter and at 1 meter from the output. And I was surprised to notice that the light actually stayed in separate beams, and the spot size didn't change at all throughout. And there was no divergence. And here you can see the graphs plotted. You wouldn't be wrong in thinking that they're the same graph. They aren't, but they look pretty much the same. One interesting thing I ran into is this Nyquist frequency, where I had a low resolution for my detector at first, and I got this weird pattern. I thought it was interference, but it wasn't. So we can see on the right that is the actual measurement. And then we have all these different measurements, which look the same again. So let's discuss, why is this? Well, first of all, the 510 nanometer gallium arsenide waveguide thickness is sensical. So looking at SOI waveguides, silicon on insulator waveguides, are 220 nanometers in height, and they have 1550 nanometer light inside of them. So the height I picked for the 0th mode waveguides makes sense. Zemax ray tracing is just not the right tool for the job, I realized. So ray tracing photons actually treats them as rays, not waves, which should have figured. The evanescence of the 1.3 micron light should cover the entirety of the waveguide, not stay in their respective beams. Well, RSOF biosynopsis, which sadly I have experience with, but wasn't available to me because it's I just don't have it. It's an FEM, a wave equation solver on the right, and it would be perfect for this simulation. I just realized that Zemax is just not good for nanoscale optics. It's great for other for macro scale optics, but not for this. So I kept going, and I also compared my quantum dot laser to other quantum dot lasers. So we have the range being 2 to 30 milliwatts, and some of these papers actually use multiple quantum dot layers stacked. I didn't, but usually they use 5 quantum dot layers stacked, which makes sense because that improves the gain. It makes the medium a little bit larger, and I should use that next time. In terms of the net gain calculation, so I got only 31.7 microwatts. I realized that this value could have been off by a factor of 50, bringing me to 4.5 milliwatts if I were to include that factor of 50. And I'll touch on that in the extra slides later, but basically this was something from where I got the equation from, and I'll touch on that in like 3 slides. So I want to conclude by saying that I've made a quantum dot laser design from the ground up. This laser's tiny, as you can see in this image made by me. It provides 1.3 micron light at 31.7 microwatts, maybe. Thanks for listening, and hopefully you learned something. Now I will proceed to explaining this gain function. So the gain function actually makes use of this gain per meter as its main parameter, and then it depends on the quantum dot planar density, the active medium width, refractive index, the Einstein coefficient of stimulated emission, the inhomogeneous line broadening, which I mentioned I used 5% for, and the electron population density difference. So the book I used, which is the 10th reference here, rank, I got a value of 50 times smaller than what he got. So basically I inputted the equation shown, alpha, or what I call G, and all the values that he gave, and I got a value of 19 inverse meters rather than 1,000 inverse meters, as you can see highlighted. So I spent several days on this and could not figure it out. So it would be nice to know that maybe I was missing something very small and stupid. So if I could figure it out, it would be great. But for now, I'll stick with my microwatt laser, and if I can bring it up to 4.5 milliwatts, that's great. So I want to thank you for your time, and hopefully this made sense. And this is actually for a school project, but I decided to upload it after I present it, just for more people to benefit from it. So thanks, and stay tuned for another video maybe.